Greetings everyone, and welcome to my channel. This is the first video of a series where we will explore a variety of concepts and ideas regarding differential calculus, as well as their practical uses in real-life contexts. Today's topic is the concept of rate of change, as the title of this video suggests. There exist two distinct types of rate of change in mathematics. The first one, which we will discuss shortly, is average rate of change. In its simplest form, average rate of change is how much a variable changes in a specific interval of time. This is best illustrated on a graph, where we have an x and a y axis. The horizontal x-axis shall represent time in seconds, while the vertical y-axis will simply be the variable that will be changed. For the sake of this demonstration, we will say it is the distance in meters a ball has traveled away from its point of origin. You may notice it is a straight line, a linear function. In this situation, the average rate of change in any interval remains identical throughout the entire line, and it is equal to the gradient of this linear function. You may recall that to find the gradient, which is often denoted as m, you must divide the difference between the y-coordinates of any 2 points on the line by the difference of their respective x-coordinates. Rise divided by run, if you will. In our case, however, we must recall that it will be the difference between the quote-unquote d-coordinates divided by the difference of the quote-unquote t-coordinates. First, we will look at the interval between t equals 3 and t equals 4. The difference of the two ends of this interval, or to word it differently, the difference of the t-coordinates, will be 4 minus 3, which is equal to 1. This is displayed with the line on the graph. It is the run. Next, we will simply find the difference between the two d-coordinates in question. 8 minus 6, which is equal to 2. Again, this can be seen on the graph with this new vertical line, the rise. Finally, we will divide the two differences as shown in the original equation, rise divided by run, and we obtain the result 2, meaning the average rate of change for any period of time on this graph is 2. We can repeat the previous steps with a new interval, between t equals 0 and t equals 6. The difference between the ends of the interval is 6. The difference between the d-coordinates is 12. And finally, 12 divided by 6 is 2, as was the case previously. Thus, we can see that the average rate of change anywhere on this line, regardless of the interval, is always the same. Before proceeding, our formula for finding the gradient, or the average rate of change, can be rewritten as follows. Delta d divided by delta t. This triangle symbol is the Greek letter of delta, which is used in mathematics, science, and other fields to denote change. Therefore, what it reads is actually change in distance divided by change in time. You may already be familiar with this formula, or its simpler variation, d divided by t, which is the formula to find the speed of a moving object. Consequently, we have found that the speed is actually the rate of change of distance, how much distance changes in an interval of time. As our time was measured in seconds and the distance in meters, the speed will be measured in meters per second. Nevertheless, graphs do not always display linear functions, which are generally easy to work with. Often, graphs display real-life phenomena, which are rather complex, though that does not necessarily imply it will become more difficult to work with. Here we see a graph of temperature with respect to time. More specifically, the average temperatures A in each month of the year. The x-axis is once again time, though now in months, while the y-axis is the aforementioned average temperature in degrees Celsius. This graph may seem daunting at first. However, I promise it is not as complicated as it may seem in the beginning. To begin, you may have realized the fact that this graph is comprised of several small straight lines. Or in other words, these are all parts of linear functions. What could be done here is to find the average rate of change in a small interval, such as between t equals 5 and t equals 6. To find the average rate of change in that interval, one must use the same formula that was used previously, though this time, instead of our variable being labeled as d, it is labeled as a. Rise divided by run, the difference of a coordinate over the difference of the t coordinates, the change of a over the change of t, whatever you want to call it. Now we must repeat the same calculations as earlier. First, finding the difference between the two endpoints of our interval, 6 and 5, as shown here, as well as the difference between their respective a coordinates, as can be seen here. We now divide 4 by 1 to find that the average rate of change in temperature from t equals 5 to t equals 6 is equal to 4. We may repeat this process once again with the interval between t equals 9 and t equals 10. I shall skip the explanations of the calculations, as I am certain it is sufficiently clear to everyone now. However, now we notice that we have gotten a negative value here, a negative rate of change. That was to be expected, as we can visibly see on the graph how the line is moving downwards and how it has a negative gradient. When the average rate of change is positive, it means that, on average, the variable is increasing in value within that interval. However, if it is negative, it is the opposite. On average, it is decreasing in that interval. Finally, instead of finding the average rate of change in a small interval of merely a month, we will now examine the average rate of change of temperature for the entire year, from t equals 0 to t equals 12. That is a rather large interval, but remember that intervals do not have to be 1 unit in length. Rather, they can be any size from any point to any other, and they may encompass the entire graph. It might seem more challenging than what we had done previously, as we have been dealing with small straight line segments. At the moment, though, we are faced with a line that looks like a horizontally reflected question mark that was rotated about 70 degrees clockwise. Yet, in spite of that fact, we will continue using the same formulas as before. Firstly, we subtract 0 from 12, which equals 12, our change in time. Secondly, we subtract 5 from 10.75 to obtain 5.75, our change in temperature. Lastly, we divide our change in temperature by the change in time, which is approximately 0.479, and that is the average rate of change in temperature throughout the entire year. Effectively, we have once again divided rise by run, and created this diagonal straight line passing through the endpoints, and whose gradient is the average of all gradients in this weirdly shaped curve. That is why we refer to it as average rate of change. It is an average of all rates of change in that interval. When you have a straight line, the rate of change is always the same. Therefore, the average will maintain that value indefinitely. Here, though, we have countless rates of change, and they all average out to this red line over here, whose gradient is 0.479. Theoretically, if you were to find the sum of all gradients in this curve and divide them by the number of all gradients, you would get this value, 0.479. In other words, 0.479 is the mean of all gradients in this curve. Generally, we look for the average rate of change of an interval we do not have much information about regarding what occurred in between the endpoints. To name an example, if you are driving a car for 2 hours and arrive somewhere 200 kilometers away, your average rate of change of distance, your average speed, will be 100 kilometers per hour, as 200 divided by 2 equals 100. Evidently, the car must have accelerated, decelerated, or even stopped at some points during the drive. It is extremely unlikely it would have driven at a constant speed for the entire 2 hours. It's just an average. However, if we do not know what happened between the point where the car started and arrived at destination, we have no other options. The time has come to discuss the second type of rate of change, the instantaneous one. As the name implies, it is the rate of change at a given instant, at a single given point, not an interval. To phrase it differently, it is how much something, like a variable, changes at a particular point. I have mentioned it previously, but the average rate of change, and therefore the rate of change in general, anywhere on a linear function, is the same, always. This means that for linear functions, only linear functions however, the average and instantaneous rates of change will be identical, regardless of where exactly they lie on the graph. Hence why allow us to return to this previous graph of distance in respect to time. Say I want to know the instantaneous rate of change at t equals 1, knowing that the average rate of change from anywhere on the line of a linear function will be equal to the instantaneous change anywhere on that line. I could simply find the average rate of change in the interval from t equals 3 to t equals 4, as we have previously done it, and it will save us time. Simply put, find rise divided by run. The result will be the instantaneous rate of change at t equals 1, and at any point on the line for that matter. Here is the formula, and here are the calculations to remind yourself of how it is done. As we can see, the gradient as well as the general rate of change of this function, that is the instantaneous and the average rates of change, are all equal to 2. Now, let us complicate things again, shall we? We have just looked at a linear function where both the average and instantaneous rates of change are identical everywhere on the line. However, that is not the case with nonlinear functions. This is part of a quadratic function, meaning it is a parabola. And one notable aspect of parabolas is the fact that they are not straight. I want to find the instantaneous rate of change, or if you will, the gradient of the function, at point t equals 4. Linear functions have a constant gradient, as previously stated, but nonlinear functions have multiple gradients. The gradient at one point will be different from the gradient at another. What we are looking for is the gradient on the line at just t equals 4 and no other point. If we were to create a straight line with that gradient and the correct y-intercept, it would intersect smoothly with the parabola at just that point at t equals 4. This is called a tangent, a line that barely intersects with a curve at one point. The point with which it intersects, in this case 4, 1, is the point of tangency. One key issue we are now faced with is how to find this gradient, and that is the fundamental question of differential calculus. How do we find the instantaneous rate of change? The formula we have used thus far to find the average rate of change is obsolete, as we have no other coordinate on this line aside from the red one there. We can't have a difference of distance or a difference of time when we only have one given point. Instead, for now at the very least, we can only estimate the value of the gradient of the tangent. To estimate, we choose a point on the line, say right there. Now we have defined an interval between t equals 4 and t equals 12. We can now find the average rate of change in that interval using the old formula, and we attain the green line shown in the graph. Our calculations yield the following result. The gradient of this interval is 1. Alright, let us repeat this process, but this time we shall make the interval a little smaller by moving the upper endpoint a little closer to the point we are looking to find the instantaneous rate of change for, which in our case is t equals 4. Let's make the interval between t equals 4 and t equals 10. As you may see, the point has shifted down the line, and we have a new gradient as a consequence. According to our calculations, that gradient is 0.875. Now we move that endpoint down even further to t equals 8, which yields a gradient of 0.75. Finally, we move our gradient down one last time to t equals 6 and get a gradient of 0.625. Now look closely at the graphs. Carefully observe how this gap between the green and red lines in the top right corner is getting smaller as we bring the upper endpoint closer to t equals 4. Essentially, the interval is getting smaller, which in turn makes the gradient of the green line and the red line, which is a tangent, more and more similar to each other. This pattern will continue to hold true. If I were to move the upper endpoint to, say, t equals 5, then t equals 4.5, then 4.25, etc., the gradients of the two lines will become more and more similar. Fundamentally, this means that the average rate of change of these smaller intervals become better estimations of the instantaneous rate of change at t equals 4. However, we must remind ourselves that they remain estimations and not the exact instantaneous rate of change. You may rightfully ask yourself, isn't there a way to get the actual instantaneous rate of change without estimating it? The answer to that question is yes, there is indeed a method. However, that will be explored in my next video. It was important to first understand this concept of rate of change, and that has taken long enough to do. The explanation part of this video is done, and we shall now move on to some exercises to help practice what we have just learned. To begin, here we have a graph of distance in centimeters with respect to time in seconds. Question A asks the following. What is the average speed, that is the rate of change, of the object between 2 and 4 seconds? Question B asks, what is the speed of the object at precisely 7.55 seconds? I strongly encourage you to pause the video and try solving these problems for yourself, and afterwards I will go over them myself. Alright, first we look at A. We may simply use the formula to find the average rate of change in the interval between t equals 2 and t equals 4. After doing the calculation, we obtain 1, or 1 centimeter per second. Next we have b. It is important to identify that b asks for the instantaneous rate of change at t equals 7.55, as emphasized by the word precisely. As we know, the average rate of change and instantaneous rate of change in a linear function are always the same, regardless of what point is in question. So we must simply take the result from our previous question, 1 centimeter per second. Next, we have a new exercise involving a nonlinear function. First question. What is the average acceleration of the object between 0 and 3 seconds? For those who are unaware, acceleration is how much the velocity or speed of something changes in a given amount of time. Just like speed is the rate of change of distance, acceleration is the rate of change of speed. Second question. What is the average acceleration of the object in general? Once again, it is recommended you pause the video and solve these problems for yourself. Afterwards, we may compare. To find the average acceleration in the interval between t equals 0 and t equals 3, we once again use the formula. This offers us the result -1/3, meaning the speed is decreasing. Or to phrase it differently, the object is decelerating. The unit for this is meters per second, or more correctly, meters per second squared. The second question simply asks about the average acceleration. When the question does not specify an interval, it means you must find the rate of change of the entire line, in this case from t equals 0 to t equals 6. We use the formula and find the average acceleration of the entire line is -2/3. That is -2/3 meters per second squared. Well, this has been my video. I certainly hope you enjoyed it and that it has helped you understand this concept, which will become vital in later topics of differential calculus. Thank you so very much for watching. If you enjoyed, leave a like and comment to maybe give me some feedback on the quality of the video itself and my teaching. Furthermore, if you have any questions, you may ask them in the comment section. Have a wonderful day and farewell.